Okay, so up until now we've spent a lot of time talking about acid-base dissociation. There's a slight differentiation between acid-base dissociation and acid-base neutralization. While a lot of the conversation that we've had about acid-base dissociation, I've mentioned that there is an acid and there is a base, and it produces conjugate acid and conjugate base. For example, we've talked about acetic acid quite a bit. So if we have acetic acid, it looks something like this. In water would produce, so this would be a dissociation. In water produces the hydronium ion plus your acetate ion. So while we have mentioned that this is considered an acid, this is considered a base, and this is a conjugate acid and this is a conjugate base, when we're talking about acid-base neutralization, we are actually talking about when we add something other than water or a better something in this case would be a better base than water to the acetic acid, so that some of the acetic acid will actually be neutralized before it even goes into what we call an equilibrium. So this is an equilibrium, and for obvious reasons it has a forward reaction and a reverse reaction. So since it has both those reactions, we consider this an equilibrium. I think I misspelled that. So an example of an acid-base neutralization then would be more like what we did in the beginning of this acid-base unit, of something like HC2H3O2, which is a weak acid, plus something better than water that acts as a base, so something perhaps like NaOH. So when we have an acid plus base, in this case, we get water and salt. So you get your HOH, your double replacement, H, and you get your other two ions together like that. So you're going to get something like this. So the water that's formed is a pure substance, so that we'll put an L next to it, so it's a liquid. And the sodium acetate, as we have learned from the previous unit, sodium is an alkali metal, and alkali metal salts are all aqueous. So basically what ends up happening is that your sodium ion and your acetate ion are floating around in water as spectators. So the neutralization reaction then produces water and a salt. But you notice that there is actually no hydronium or hydroxide present in this specific reaction mechanism. Another example of this would be if we were to write ammonia. So let's do another example of one that's a base. So say we have ammonia, which is a weak base, and a strong acid. So you have your H, so this is a base, this is an acid. So HCl is a better acid than water, and ammonia is a better base than water. So even though this is all happening in water, the best acid and the best base will find each other and react. So this reaction actually will happen before the remainder, whatever's left over in the water, will participate in a dissociation with the water. So this H plus will first neutralize this ammonia. So you'll get something like ammonium ion, and then you'll get your chloride ion floating around in water. So it works exactly the same way, but instead of using water as the other acid or the other base, we're going to use something stronger. And what we end up getting is we call this a neutralization, because the best base and the best acid will react first before whatever's left over will go into equilibrium. So take a minute now, and I want you to practice writing a neutralization reaction for the following. Write the neutralization reaction, not the acid-base dissociation, for C5H5, my fault, C6H5, C6H5, NH plus, which is an acid, with a base. Let's try to do LiOH. So take a minute, pause this, and see if you can figure out how the rest of this neutralization would look. Okay, so if you were to write this as a neutralization, we have this as my acid, so we have an extra proton here, and as this is our base, so this is the extra, or this is the hydrogen acceptor. So my hydrogen is going to work on it over that way, and then we will get something like, moving that hydrogen over, you get C6H5N. The H is now moved over, and now you get your H2O, and then a lithium ion that's floating around in water. Okay? So it's very similar to what we were doing with the water, except for we're going to do a chemical reaction with the best acid and the best base possible. And then afterwards, we'll figure out what's floating around in the water and figure out what the pH is. So let's do an example of that. Okay, let's try this problem. So what is the pH of a solution formed after adding 20 milliliters of a 0.1 molar solution of sodium hydroxide to 50 milliliters of a 0.2 molar solution of acetic acid? This is a lot like the titration that we were doing, but this is what is the pH when we're not at the equivalence point. So one of these is going to be left over. So either the sodium hydroxide is going to be left over floating around in water, or the acetic acid. So you can think about it kind of like some of the acid or some of the base is going to get knocked out from the other because of the reaction with the neutralization reaction. So the first thing that's going to happen is your sodium hydroxide is going to react. So my first thing would be a neutralization reaction. Ways that you can tell that this is a neutralization reaction: if there is a better acid and if there is a better base than water, the better acid and the better base will actually react first, and then whatever's left over will then interact with the water. So since we have sodium hydroxide and we have our acetic acid, the acetic acid will react with sodium hydroxide first, and whatever's left over from this combination is then going to go into equilibrium with water or go into a dissociation reaction. So the first thing that happens is a neutralization reaction. So this is my base, my best base, since sodium hydroxide is definitely better as a base in water, and my best acid, which is acetic acid, and acetic acid is better as an acid than water, so we've got better candidates here. So the acid is going to react with the base. This is an acid, so I have an extra proton, and this is a base, so I have a proton acceptor. So my reaction will then be HOH, and then everything else that's left over, which is my sodium acetate. So we have our neutralization reaction that looks something like this. You have your water, and you have your salt. And then the second thing that will happen after this occurs, then whichever part is left over, if I have acetic acid left, or if I have acetic acid left, then we'll have a weak acid that goes into equilibrium. If we have sodium acetate left, then we'll have an acetate ion, which acts as a base left in water. So let's figure out what's left over. And this is basically just a normal stoichiometry problem. So if we have for sodium hydroxide, the given information, I have 0.1 molar, and I have 0.02 liters. And for acetic acid, I have a 0.2 molar, and and 50 milliliters is 0.05 liters. So if I was to figure out how many moles this is, so we know that molarity times volume is moles. So I'm going to take the molarity of the base, which is 0.1, multiply that by 0.02, and I get 0.002 moles of base. And I have 0.2 times 0.05, and I have 0.01 moles of acid. It doesn't necessarily matter that I have a weak acid and a strong base here. It just matters that I have an acid that's better than water. So sodium hydroxide will react with the acetic acid, even though it's not completely dissociated. So we can talk a little bit more about that in class, but just treat this as a normal stoichiometry problem. So we can see from our two values here that since it's in a 1-to-1 ratio, all the coefficients are 1, right? I have more acid than base. And how much more acid than base do I have? I have 0.01 minus 0.002. That looks terrible. 0.002, because it's in a 1-to-1 ratio. I will have 0.008 more moles of acid than base. So at the very end of this problem, if I have 0.008 moles of acid, and this is of acetic acid, let's remember that, I have 0.008 moles of acetic acid. If I know the concentration, then I can, from this point on, it's just the same problem that you've been doing. So let's make note of the volume at 70 milliliters. So if I have 0.00, continuing on, so now I know that after the neutralization, there is weak acid left over. That means that I have C2H3O2. This is more, so the sodium hydroxide gets completely used up, and there's acetic acid left over floating around in water. So after neutralization, there's going to be a acid dissociation, or an equilibrium that will be established from the acid in water. So you'll have your acetic acid, you have your acetic acid, HC2H3O2. So after neutralization, there's 70 milliliters total, the total volume, because it was the 20 milliliters and the 50 milliliters together, and I have 0.008 moles of acid after the neutralization. This is going to then react with the water. So the sodium hydroxide gets knocked out by the acetic acid, and whatever's left over is going to go into a normal, what we have been doing, dissociation with the water, to produce. So since this is now a reaction with the water, the second ingredient here is going to be H2O. So remember, all the way back in the beginning of this little lecture, I mentioned something about how the best acid will always find the best base to react with. Since sodium hydroxide has now been completely used up, the best base possible, or the best base available, is going to be water now, because sodium hydroxide is gone. So the neutralization here, or it's not really a neutralization, it's more of a dissociation. The reaction will still be similar in that this H is going to now move over to the here, and so what you'll get is not water, but you will get an H3O+, because it's going to split up the water molecule. So this is review, and then we just do a normal problem from here on out. So my 0.008 divided by 0.07, my new molarity here is 0.114, and if I want to know the pH, we do the same thing. We're going to set up an ice table, and this is 0 to start, 0 to start. So after the neutralization, it's as if it's like resetting. So then you get a certain amount of acetic acid left over in terms of molarity. Remember, it has to be in terms of molarity. And then it will establish a new equilibrium. So then it's going to be this minus x, and then you know how to solve this. So it would be, and then the Ka is 1.8 times 10 to the negative 5 for acetic acid. And you'll learn to memorize a couple of these. We're going to ignore the x, so then your math becomes a little bit easier. Square root of that. So then you get an x value that 0.0014 is x. And remember, x is equal to your hydronium ion. So at this point, it just becomes the exact same problem. And then the negative log of that is going to be 2.8. So the pH is 2.84. So this makes sense, since we had initially more acid than base. That means that the pH should be less than 7. Since we have more acid, after the base is going to be used up, there's going to be acid left over. So if there's acid left over, however much acid that's left over will then participate in an equilibrium with the water, and the pH should be low because there's not enough hydroxide to knock the H plus out. So this makes sense. Hopefully this is a good introduction to what we're going to be doing next. So we'll be going from acid-base dissociation to neutralization, and obviously you can see the implications of titration here, because as you add different amounts of base, we'll get different pHs, and that S-shaped curve that you guys generated before, we'll be able to calculate the different pHs along the way based on the different volumes that we added of the base. So that's where we're headed. Hopefully this is somewhat clear, and I will see you in class.